Hello, this is Paul from First Attack. In this lecture, I will going to introduce a very important concept. We call it differentiable. To determine if a function is differentiable or not at a specific point. And the definition is here. We say a function f is differentiable at a if the derivative of a or f prime a exists. So what is differentiable? Differentiable, which means derivative, right? If it's derivative, then it's differentiable. Derivative, which means this limit exists, right? Of course, we have another form, which is f x minus fa over x minus a when x approach a exists. It's the same. And what does this really mean? Okay, and in this video later, I will going to introduce the meaning of a differentiable. And then we have another definition. If f is differentiable on open interval, what does this mean? This means is the function is differentiable at every number on the interval. Okay, so at every number differentiable, then f is differentiable on interval. And we're going to show one example. Okay, so do one questions to discuss when or where the function is differentiable. And we're going to look at this question. So we have absolute value function, right? So absolute value function. If someone remember the graph, I will going to draw the graph first. And this is a piecewise function. We have two pieces. Okay, when x greater than 0 is y equals x. When x less than 0, y equals negative x. If I draw the graph, should be simple like this. Okay, and it is a condition system. The right side is like this, right? Okay, the left side is like this. Okay, so this is the absolute value function. So how do you discuss this is a piecewise function? So we have the left piece and the right piece. Imagine, okay, so first we explore. On the left side, any point, do you think the derivative exists? Yes. What is the derivative? The derivative is the slope of the tangent line. Give a point, the tangent line is the self, right? So it should be -1, which means on the left side is differentiable. Why? Because the derivative exists, -1. How about the right side? Any point given, do you think is differentiable? It does the derivative exist? Yes. Why? Because the slope is this, right? The self. The tangent line is the self, so the slope is 1, which means the derivative exists. Okay, it's the second. One more. How about the boundary point? Okay, how about this point? Probably someone you will think, no, is this differentiable? We're going to find the derivative. What is the derivative? Is y equals 0, or y equals -1, or y equals 1? Probably we are wondering. So we are going to show, and that the function is non-differentiable at this point, and the differentiable at the left side, and the differentiable at the right side. Okay, so we have 1, 2, and 3. So I will going to show how to organize. We have to use the definition. So is this the first we look at the left piece. Okay, we need to verify the limits exist, the derivative definition. Okay, based on the derivative definition. So the first we're going to look at all the x less than 0. Okay, so which means the left point, and we're going to see the definition. What is the definition? F prime of x is this, right? Is the limit we use h approaches 0. It is. Okay, and the f x plus h minus f at x, right, over h. That's the definition. We're going to verify. Okay, see, and this limit should be equals -1, as we discussed at the beginning. Why this equals -1? we just do calculation, right? When h equals 0, so x is any negative number. Of course, when h equals 0, h is small enough. Therefore, x plus h should be still a negative number. You think about it, this negative number, put the absolute value should be what? Should be go to the opposite. So therefore, I put it here, the opposite of this. So this is positive now. And the x negative, put the opposite value should be negative x, okay, which means minus negative x. So this we plug into the value, then over h. Okay, we're going to simplify and to find the limit. What do we find? This is easy. Negative x plus x is so we cancel x, right? And then h over h. So we don't need this. Let me see. There's h over h, right? Directly. Okay. Oh no, the h is negative h because here negative. Let me write it one more. Negative h, and then now this is easy to do the calculation, right? So I simply say, so I need to cancel all this. We don't need this so long. Let me write it here. So should be equals what? Equals negative 1, right? The limit h approaches 0, negative 1. Negative 1 had the limit equals negative 1. Okay, so this is what we say, right, at the beginning. Okay, any point is differential because the derivative is negative 1. Okay, so we can make a conclusion. Now for any x less than 0, what do we say? So we can make this conclusion. So f is differentiable. When x for any x less than 0. Okay, so this is the first, which means the left side any number is differentiable because the derivative exists. We base it on the definition. Now the second, okay, do you remember the second we discussed the right sides, right? Okay, we're going to find the right sides. The second part we're going to discuss for any x greater than 0. See what will happen. We explored, right, the derivative should exist equals 1. Does this really true? We're going to just do calculation based on the definition. Here is the definition, right? Still fx plus h minus fx over h. Okay, and do calculation. This time x is greater than 0, h equals 0, so h is small enough, therefore x plus h is still greater than 0. Put the absolute value, which means up. This is a positive number, but the absolute value is still itself, right? Just do this. Okay, so x is greater than 0, so this is just minus x. Okay, and if you like, you can put a parenthesis, no matter. Okay, so we simply say x minus 0, h over h is 1. Therefore, what do we get? We get the limit h equals 0, h over h, which is the limit h equals 0, 1, and the limit is 1. Can you see this is exactly what we explored? Okay, and which means what? This which means x any x greater than 0 derivative exists, therefore is differentiable, right? So we can make this conclusion. So f is differentiable. For any x greater than 0. For any x greater than 0. See, this is the second part. Now what do we have is the last part. So how about the x equals 0? And we just discussed should be non-differentiable, right? So we're going to verify that's true. Should be for x this time equals 0. What do we have? The derivative Okay, we look at the definition. H equals 0, f 0 plus h, right, minus f at 0 over h did the definition. We put the function in. See what do we find. So here is absolute value 0 plus h minus absolute value of 0 over h. What do we get? And there's h over 0, the bottom is h, the top is absolute value of h. How do you think about the limit? This limit does not exist. Why? Because when we look at the left, it's -1. When we look at the right, it's 1. Why? Let me write it down. Because we look at the left-handed limit, which is h equals 0 from the left. And we look at h over. If x is negative, this is negative. Can you see? And here's negative h over h. What does this mean? It's -1, right? Okay, did the left-handed the same. We go to the right-handed limit. You will see what do we get. We get the limit h equals 0 from the right. So this time is h over h. Of course, is 1. The left does not equal limit the right, which means what? Okay, so this means the limit does not exist, right? This means this limit does not exist, which means the derivative. This does not exist. Okay, the derivative does not exist, which means non-differentiable, not a differentiable, right? So we make a conclusion. So f is not, or usually we say is a non-differentiable. Differentiable at x equals 0 or at 0. Okay, so these are the 3 parts. Now you know the left is differentiable, the right only x equals 0 is non-differentiable. And later we will go back to this example. You will see what is the meaning of non-differentiable or differentiable. Okay, so now we're going to explore the properties for differentiable function. What does differentiable really mean? So here we have a result, a theorem. The theorem tells us this: if f is differentiable at a, then f is continuous at a. We are going to prove it, okay? Which means what? Differentiable is stronger than continuity. Okay, stronger than continuity. So how about the converse? The converse is false. What does that mean? Given you continuous, we cannot get a differentiable. For example, do you remember we just did? This is the absolute value function. Is it continuous at 0? Yes. But we just proved, right? We just find, and this function is non-differentiable at 0, which means what? Continuity cannot get a differentiality, okay? Cannot. So differentiable is much stronger than continuity. Now let's going to prove, okay, a little bit. We can prove if differential, and then we can find the continuity. So here is a little first. Can you see? So suppose f is differentiable at a. We use the definition. This limit should exist, right? Okay. Then we're going to see it's easy to find f is continuous. Why? Because can you look at this? And this is a fraction. Look at the denominator. When x approaches a, x minus a approaches 0. The denominator is approaches 0, right? So we can find how about the numerator? The numerator should approach 0. If the numerator does not approach 0, approach to any number, do you think, how do you think about the limits? Any number, if positive number to go to positive infinity, whatever goes to infinity, right? Okay, so we have to definitely the top should be approach 0. If the top approach 0, which means the limit of f should be equals fa. The limit of f equals a, that's the definition of continuity, right? Let me write it down. This stuff we just explored is here. So we say the numerator should be has the limit 0. Of course, if we're going to detail, it's like this, because we can make a little bit that this limit equals this times this, right? Because when you cancel this term and the bottom term, you get it, they are exactly the same, which means we just divide it by term and then times another term. And now we look at it, we have one term, two term times together, so this is the product, right? We have a product law of the limit. So we're going to, this limit is the first limit times the second limit. The first limit is exactly the divisor, exists a number, right? The second term, you know, the limit is what? Is 0. Therefore, this limit is divided times 0, see, is 0. That's what we exactly see. The top goes to 0. If the top goes to 0, we just say the limit of f should be equal to fa. If you need some detail, it's like this. Because the limit is the limit of f is the limit of f minus the term plus the term. If we cancel this term, they are the same. And then we use the sum law of limit. The first term limit plus the second limit. The first limit is 0, we just proved that, right? The second limit is itself because constant, and therefore the limit equals fa. That's what we see. So the limit of the value of the function equals the value of the function at a, which means this is what from the beginning to the end. This tells us f is continuous at a, right? If you go back to review the definition. The definition, we have 3 points. First, we can define fa, of course, is defined. The second, the limit exists. Yes, it exists. Exists what? Equals to the value of the function at a. Therefore, the 3 conditions satisfied. Therefore, is continuous. See, so far we have results. If the function continue, if the function is differentiable at a number, and then the function should be continuous at that number, right? Okay. I'm going to explore a little bit more. We're talking about the non-differentiable. What does it mean? And I already list to you how many type of not differentiable. Non-differentiable. We have only 1, 2, and 3. The first is discontinuous. For example, the first. And we think we just have a theorem, right? If the function is discontinuous, definitely, okay, it's non-differentiable at this point, because we have a theorem. If it's differentiable, should be continuous, right? Not continuous should be not differentiable. This definitely, okay. We have a jump. If we have a jump or gap or whatever, not discontinuous or not continuous, is non-differentiable. The second corner, what does it mean? So this is corner. We have a corner on the curve. This is very sharp, and in this case is non-differentiable. Do you remember we have the first example at the beginning? We have an absolute value function. Do you remember the graph? Is a sharp, is a corner at x equals 0, right? When we meet the corner is non-differentiable. Why? Because the derivative does not exist. If we look at the limit, if we look at the limit definition, okay, or we look at the limit. If we go on to the left side, look at the limit should be what? The snowball from the left side should be, see, and the snowball should be increased, right? Okay. The tangent line should be goes up. Therefore, if we look at the left side, the derivative is positive. If we look at the right side, can you imagine? Okay, the tangent should be goes down, which means what? The slope is negative. of course positive cannot equal negative, right? Therefore you can see there's no slope, okay, no tangent line found at this point, which means the dividable definitely does not exist. Imagine as the first example we did. So if you look at the corner, that means a non-differentiable. One more, the last. So this looks very good, but if we look at the tangent line, and the tangent line is vertical tangent line, which means what? The slope goes to infinity. The slope does not exist. The slope does not exist means what? Which means the derivative does not exist. Okay, does not exist, which means non-differentiable. Okay, you put all these three together, it's only either discontinuous, or we have a corner, or we have a vertical tangent line. No other options. Okay, so at the beginning we say now we can understand what does differentiable really mean. See, this is non-differentiable. So what is differentiable? Differentiable means the curve should be continuous. The curve should be no sharp corner, smooth. The curve of the function should be what? No vertical tangent line. Okay, we put all these together. Usually we call, if the curve of the function is very smooth, then it's differentiable. So smooth curve is differentiable. Smooth, of course, should be continuous, right? Look at the last example. Can you see? If we have this graph, can you tell us which point is non-differentiable? Of course, smooth, except the 2 points. Other points are very smooth. See, the first point that we have what? We have a jump. This jump is discontinuous. If discontinuous, that's non-differentiable, right? The second is we have a corner at 2. Right, if a corner is not smooth, okay. If we put it together, it's just like this. And all we need is the non, and the differentiable point is this. We find is easily to find differentiable point. We have a 2. The first is x equals -1. Which type? They ask with the reason. Okay, the reason is this is a discontinuous point, discontinuity, or you say discontinuous. The function is discontinuous at this. The second is x equals 2. What the reason? Because this is a corner, right? A corner. That's